the Q&A, and hopefully Takamasa can stay with us to answer the questions.
Okay.
Okay, so thank you very much.
Thank you very much.
Okay, so our next speaker is Andrew Lorenc, who is at the Met Office and is an expert in data assimilation for numerical weather prediction. So in many ways, I guess we've got a nice theme going in this session. It's going to speak to us about, sorry, I had it here a moment ago, about Ensemble data assimilation systems for convective scale numerical weather prediction. So Andrew, and if we just remind everyone, you can put questions in the Q&A as we go, and if we have time at the end, I can put those to Andrew, and if we run out of time, hopefully Andrew can stay with us to answer them after his presentation. Thank you, Andrew.
Okay, thank you. I'll get through this in half an hour if I can. So I've, oh, it'd help if it moved on. Okay. Here's the outline of my talk. I'm going to talk a little bit about my history in DA and sort of why you should believe me. And in particular, why I've watched the development of NWP, and I've got some information about what's helped NWP over the last few decades. Second point is why we can't continue in the same way, which I think is one of the reasons we're in this meeting, and one possible way forward, the way that we seem to be going. And from that, talk about possible future DA methods, building on the current methods. And again, some of the possible alternatives. So this is my history at the Met Office. These are the computers that have been used at the Met Office. And I started on the KDF9, way back here, and I've worked on all of them. So I've got a good history on that. And you see the Moore's law curve on there in red, showing the growth in power. And during that time, again, I started back here. It didn't start going down because I joined the Met Office, but I have been in the Met Office for the period that is improved by a day a decade in the score, you know, and the Met Office and other centres have shown the same. I think it's a phenomenal improvement on the forecasts that people don't really realise that in global NWP, the 5-day forecast is now as bad as the 1-day forecast was when I started. So that's the background. I've been working in NWP in all this time in various places, and so I've been close to, including some international committees, close to sort of consensus of what the causes of the improvements were. And obviously computer power, increased resolution, and the Met Office went from, improved steadily, but 150 kilometres of what we had in time of at the time of the Falklands War, and 10 kilometres was the grid spacing we had a couple of years ago. So that's a big improvement and carrying on down. And as I said, they're down to 3.5 kilometres in experimental ensembles. The computer power also went on longer forecasts. Obviously, if we got better, we could go longer, and ensembles for forecasts. So that also multiplied the costs of running. So from running a few days of one best estimate, we now run weeks of a whole ensemble. And then, of course, better forecast models and better DA methods. And the money spent on DA has gone up from about a factor of 3 to a factor of 50 to 100 of the cost of running the model. So we are spending more on DA now than we were. And the biggest individual improvements came from data assimilation, and they can be classified into 3 types. The first one, the biggest one, I think, most important, was the Bayesian weighting of the observations and the prior. Back in 1979, when we had the FDG, the global weather experiment, this wasn't really there, and people were, the idea was that you drew to the observations. You know, you talked about a first guess, but as soon as you had an observation, you corrected the first guess. And it was only in the 1980s we realized that the background had 80% of the information and was actually normally more accurate than any individual observation. And so you had to weight them. And particularly when you come to satellite radiances, which have got a funny information content, you really have to do that very carefully. And that change really was the springboard for getting better. Then we improved the Bayesian methods to use linear models and or ensembles, and either the ensemble Kalman filter that we've heard talked about, or 4D VAR. And in the global model, 4D VAR has been the favorite, so I'll focus mainly on that, to predict the evolution of errors actually inside the DA window. And that was a big improvement in the decade that I've got there, start of the ECMWF. And then moving on from that, the next decade really, the THORPEX experiment, international collaboration, where they were looking at sort of methods of predicting where the errors would be. And that evolved into actually using the ensembles to estimate the flow-dependent growth of forecast errors and using that in data assimilation. So those are the three big improvements that we've had. And as I say, those three together have really got us a system that is doing remarkably well compared with what it was 40 years ago. It's really one of the successes of the computer age, to my mind. But we can't expect the improvements simply to continue using similar methods as the resolution increases to convective scale. And that's the main point I want to make. And it's a bit of a shock, because a lot of people, particularly the modelers, say, yes, we have the new computers, we can make the models run down to convective scale, just carry on doing the same thing at convective scale and all will carry on working. And I want to say that it won't. And to do that, let's talk about the methods we're using. And I will talk about the 4D VAR method, because that's one that's been most popular in global NWP, where in principle, it's quite simple. You use a model to forecast in time over a time window, and then an observation operator to forecast what the observation is going to be. And then you determine a best fit between the observations and the background. Assuming Gaussians, you can do this, and this is the equation that comes out. So this is the Bayesian equation for combining observation information with prior information. And the technique we use in 4D VAR to find that best fit, and the size of X is about 1 billion. So it's a very big minimization, but we have to use a gradient and a descent algorithm to find the minimum. And that's a theory. And you end up pictorially, you have a Gaussian prior that you're assuming here in 10 to the 9 dimensional space. And you try one run and you say, oh no, downhill it goes there, 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 and you search for the best estimate. And because the equation is nonlinear, even though that starts with a Gaussian, that descent is not actually a nonlinear descent. It's hard to do because of that, and no guaranteed minimum, and it's expensive to run all these models at high resolution. So nobody does it that way. That would be too expensive. You cannot run with the best available computer model, which always expands to fill the available computer. You can't run all these runs at the full resolution in the time that we've got. So the thing that's made 4D VAR affordable is to have a perturbation, an incremental approach, where you have the full model as before, but then you have a linear approximation to perturbations to it, which is done at lower resolution and a simplified model, and it's cheaper to, much importantly, cheaper to run. So one thing, this makes it cheaper to run. The other thing, it makes it easier to solve, because you then get a quadratic problem, and so things stay Gaussian. So looking at that pictorially, this then comes down to a much more clearly Gaussian Bayesian way of doing things, and it maps onto the Kalman equation that is used in the Ensemble Kalman filter, which is doing the Ensemble Kalman filter is doing this same equation, but forecasting it with an ensemble. Here we're forecasting it implicitly with this linear model. So you start with a Gaussian at the beginning, and you implicitly define a 4-dimensional Gaussian using that linear model. And then the 4D var is, again, minimizing to find the best estimate, the best fit between the prior and the observations. So why can't current methods work for global convective scale models? Last episode I talked about the convective scale, not what Miosha was talking about, the very small scale. Models, our current models have got more than 10 to the 9 degrees of freedom. I haven't counted them recently. It was a few years ago, it got up to 1 billion. Bayesian methods need to consider, in principle, they need to consider a PDF with these dimensions. Now, I don't know if you can ever get your head around a 10 to 9 dimensional PDF. It's mind-boggling. And that suffers from the curse of dimensionality, which means that even if you had a 10 to the 9 ensemble members, they would not be close to each other in that PDF in general. Any two samples are always a long way apart in that sort of dimensional space. And so no statistical methods that rely on closeness or sampling will work in that sort of dimensions. And in that sort of dimensions, the other thing comes in is the butterfly effect. We all know about chaos and think of relate butterfly effect to the chaos, but the butterfly effect is more than that. It's to do with the resolution. It's to do with the fact that the small scales become chaotic much more quickly, and there's always smaller scales that will feed chaos at the smallest scales, and that will cascade upwards. And so there's always some small scales which are likely to be chaotic and poorly sampled and therefore non-Gaussian. So the general case has no hope of ever being sampled and manipulated. And current NWP methods consider scales which are well forecast and observed, so errors are small. And we can make the Gaussian approximation. And the big advantage of that, and the thing that everybody does implicitly, and they don't even mention it, Spectromatter didn't even mention it, is that you replace the Gaussian assumption is necessary to make the whole thing work, because you can replace the billion dimensional PDF by a billion by billion matrix, which is still huge, but that's conceivable. You could almost think about event one day stop it. And further assumptions, further approximations, going to slightly lower resolution, make it then practicable. And that's what we do with the various DA methods. And the difference between the DA methods, either Ensemble, Cameron, Filter, or 4D var, is in the assumptions that make this thing doable, all being based fundamentally on the Gaussian approximation. But there are not enough observations at the global convective scale. And as I said, errors grow because of the butterfly effect. So forecast errors are not all small. And so there will be scales that are not well represented by the Gaussian and can't be handled in this way. And just to show you, this is the latest product of 500 data volume. The only point I'm making here is on a linear scale. And all the previous things I had about computer power, and I didn't plot one model resolutions, were on a quadratic scale, on a logarithmic scale. So this is not increasing anything like fast enough to keep everything well observed on a global scale. Of course, locally you've got radars, and for local scales you can do it. So one way forward for the global scale is to change the objectives. And I think we're already doing this, but we've got to understand why. So most useful forecasts don't require high resolution accuracy, if you mean sort of very fine resolution. You can make a probability forecast for significant small scale weather, which can be reliable for a region without being able to predict exactly where and when in that spatial and time period, spatial region and time period, the severe weather will occur, and that's still very useful. So that's a sort of way you've got to build the forecast systems, and you've got to measure them that way. And we're doing some work now on measuring our forecasts that way, which I'll talk about in the next slide. So that's one brick of the change we've got to make in order to carry on getting better forecasts. You've got to change how you measure better. And the the other thing we've got to do is generate the chromatology of the high resolution weather, even if it's not in the right time and place. And you might do this with, if you've got very specific things like high rainfall, do it with machine learning. But that is so flow dependent on a global scale on different weather systems, different types of weather, that I don't know yet of any machine learning system that can actually generate everything from fronts to convective storms to typhoons, tornadoes, tropical cyclones. All that sort of weather can be generated by a good climate model, even if it's not in the right time and place. And so what we can do is use the convective scale global models to do this in the climate mode. So what we need to develop is data simulation methods that build on and use our current models, using the current Bayesian methods and Gaussian approximations for the scales which are well observed, but allow the models to develop a sample of plausible high resolution weather where we haven't got observations. And that's the challenge that we're currently working on, and I don't think it's yet solved. So that's what I hope this meeting might get some new ideas on. So quickly, let's come down to the how the sort of hard case, real example. Well, this is a made-up example, just to explain the difficulty of high-resolution forecast giving good climatology but bad forecasts. So suppose you have this radar with rain at 6 points in a 5x5 array, and a forecast which also got rain at 6 points in a 5x5 array. And in this made-up example, they're all wrong. They're all in the wrong place. So the score for this forecast would be wrong in 12 squares, whereas a no rain forecast would only be wrong in 6 squares. So this forecast, if you measure it traditional scale, traditional ways, so point by point, this forecast is considerably worse than a forecast with no rain at all ever, which is obviously not realistic. So this fractional skill scores was developed in order to overcome that, what's called the double penalty problem. And what you do is you count the number of raining squares over a threshold in the OBS. You count them again in the forecast, and then you score the two against, compare the two. You convert it to a skill score by normalizing, and then you plot the score against the averaging area in order to see what sort of scale you start getting improvements, getting skill. And this is a real example from a few years ago now, comparing a 4-kilometer model and a 12-kilometer model over a whole year at the Met Office. And you can see that right down at the smallest scale, the 4-kilometer model did not add any value because it suffers from the double penalty problem. But at intermediate scales, you did get value from the from this fraction skill score, estimated by the fraction skill score from the high resolution model. So that's the sort of thing. The difficulty with that sort of score, it's very hard to use that as a optimization measure in something like VAR. That's impossible, as far as I know, or any data assimilation algorithm. So we use this to verify what we've done, but it's very hard to use it to design what we do, other than really by careful thought. So possible future data assimilation methods that would work in this sort of environment. Right? Current DA only works where the area PDF is small. So the first is to only attempt high-resolution NWP for regions where there's good coverage of OBS, e.g. from radar, and that was the previous speaker was showing that's then a very worthwhile thing to do. And we can carry on with the ensemble camera filter type approaches. The second one is to use an incremental DA scheme, and I showed you what that was in incremental 4D VAR, where the 4D VAR only addresses the well-observed scales, but it adds analysis increments to a higher resolution NWP models. And then the model actually is left to develop almost a sort of climatological correct distribution at the smaller scales. And you're not assuming that they're going to be precisely right, but they're going to be realistic. And obviously you then need an ensemble of such models. So that's our sort of current strategy with 4D VAR. And for ECMWF, for instance, going to ensemble to 4D VAR to do precisely that. Within that, and I mention this because it's a lot of work has gone into it. It's been one of the themes of my career over the last few decades, is to allow some non-Gaussianity into the data simulation problem. And as Technically illustrated, for moisture, things aren't Gaussian. For other things, things aren't Gaussian. And we can modify the Gaussian data simulation to take some account of that for quality control, for clouds, for rainfall. That improves results. It doesn't tackle the butterfly effect type of high resolution. So it's a way of improvement. So that's why I'm not going to say much more about that. The other thing you can do, and the other thing that we're actually working on, and I can show you some results from, is working on downscaling the global model to provide regional high resolution models, because that practically operationally we can only run convective scale models at in the regional scale. So one of the things we can work on is working on how to downscale the global model to allow the regional model to spin up high resolution detail while still following the global model in its evolution of the synoptic scale weather. Or instead, there are other approaches which attend the particle filter, and I need to mention to seek fully non-Gaussian methods such as particle filters. And I won't say much more about that other than say they're. So this is my one slide about, say, about half my career is dealing with nonlinearities in 4D VAR. And I could talk for another 2 hours about each of these, but I won't, other than to say that there are ways of getting some nonlinearity in, and there's a lot of ways of doing these things. But even with these additions, 4D VAR remains a quasi-Gaussian method, quasi-Gaussian, relying on errors being small. So the advantage of this just is that we can then use observational operators that are non-linear in particular. That's been a big focus of my work, because a lot of the observations to do with cloud and rain, which are the really meaningful ones for what we want to do, which is forecast cloud and rain, are non-linear. So here I've got some results about adding realistic convective scales. And this is work in progress, and it's just not got there yet, but I thought I'd show it anyway to show the sort of things that we're doing in a practical NWP center to look at downscaling. And obviously in the downscaling it's not just used in NWP, it's used in regional climate models, where you run a global climate change model for decades to measure the effect of changing CO2, for instance. And then you want to see what does that do to local weather at high resolution. And so what they try to do is nest into that a high resolution model, which then spins up plausible weather over, for instance, the UK. And this is the area I'm considering, by the way, the UK area. So we've learned from a long history of doing that many people force not only the boundaries, but also the large scales everywhere, because it's not quite clear if you just force at the boundaries, there's some complicated relationship on how it propagates into the middle, and whether the middle will stay controlled or will go off and do its own thing, and whether you want it to. So by forcing the large scales everywhere, I think it's more consistent, more control of what's going on. But the problem with doing that, and this is an experiment where we started trying to do that in an NWP context, is that if you don't do that, if you just nest and don't do a data assimilation, in an NWP context, it's more complicated because the forcing model isn't a climate run, which is just evolving. Every 6 hours, in our case, it's incremented using the global observations, including the observations not seen by the regional model. And so you get a jump every 6 hours. And so the jumps come in. And we're trying to overcome those jumps. But the problem is that currently, with our system where we just take a particular selection of large scales and force them into the model, the rainfall in the regional model is suppressed. And this is to do with the fact that rainfall is largely a small scale phenomenon. And it's a very close, very important and good measure of how successful it is at getting the detailed weather right. And we're not quite there yet, because when we switch on the boundary nudge, the large scale nudging, it suppresses the rainfall in the regional model. So that's not quite there yet. So I thought I ought to say something about particle filter approaches and machine learning approaches. And I think alone, they won't fly. They won't come close, in my opinion, to the big improvements. Now, perhaps I'm just biased here for my 40 years work, but we've made such important strides and got such a good system over the last 40 years. It seems a pity to throw it all away and say, oh, well, no, we're going to do it a different way. So I don't think either the particle filter is a way to replace the Gaussian approaches, or machine learning is a way to replace NWP. I think they won't get there. That's my old man's opinion. But what I would say is that, well, this is my summary. But what I would say down here is that practical DA methods can build on the current methods and use those new methods, particularly machine learning, to improve the data assimilation, to make it quicker, to treat model error within the DA system and that sort of thing. And there I think there's a big lot to be gained from the new machine learning approaches, as well as in the propagation of errors. But the general summary is that the day per decade improvement in NWP were due to higher resolution and Bayesian methods using Gaussian assumptions. And we can't continue as we are to forecast accurate convective scales because we haven't got observations in the global model at convective scales. But we could use realistic but inaccurate detail to improve probability forecasts. We've got to revise our systems of evaluating and developing NWP to do that, and that will be a complex thing to do. But then the practical method can build on the current methods. And my final thing for what is the challenge is the complexity, because we've already got an awful lot of complex systems in our current methods after 40 years. Adding machine learning, and as well as we're adding oceans and land surface, ensembles, high resolution, low resolution. It's getting a highly complex system, and it's getting beyond the wit of one man to comprehend. So I'll stop there.
Thank you very much, Andrew. It's very interesting. We have a question in the Q&A, but in interest of time, I'm wondering, Andrew, if you could take a look at that.
Okay, I will have a look at that.
And in fact, it's very much on point 2 of your summary. So once you've answered that, the rest of the attendees will be able to see the question and the answer.
Okay.
Okay, so